Okay.
Okay, so a very good morning to everyone present here. I hope you are finding this certificate course on data analysis both engaging and enriching. It is our pleasure to welcome you all once again as we continue our journey through the statistical foundation of Zoology and Director of the School of Environmental Studies.
What happened? Hello, Savinder. Okay.
Uh, Sorry for the interruption. Actually, there is some update on my laptop. That's why I have to join from the mobile as well.
No problem.
Sorry, sir.
Okay.
So, a very good morning to everyone present here. I hope you are finding this certificate course on data analysis both engaging and enriching. It is pleasure to welcome you all once again as we continue our journey through the statistical foundation that underpin meaningful research. At this juncture, I have the distinct honor of reintroducing our speaker second time after the kickstart of this course, Professor T.R. Rao, who will be guiding us through the topic test of hypothesis. Professor Rao is a distinguished academician whose contribution to ecological research and statistical education span over 6 decades. He hold
Savinder, you got this introduction. They got introduction to me in the first lecture I gave last month.
but sir,
Do you
it's my duty.
huh?
Yes.
Simply up to
Okay,
you.
I will sort it. Okay, I will sort it, sir. Already I have. I'll,
Sure.
okay. So, Professor Rao hold a PhD in statistics from the University of California, Irvine, and his academic journey is further enriched by degrees from the University of Hawaii and Andhra University, reflecting a truly global perspective that continue to shape scientific thought. His tenure at the University of Delhi included serving as head of the Department of Zoology and director of the School of Environmental Studies, roles through which he influenced generation of scholars. He had also held esteemed position as visiting professor at IISER Mohali and IISER Brampur, where his teaching has been especially impactful for students and early career researchers. A passionate educator, Professor Rao had made biostatistics a cornerstone of his teaching legacy. His, his methodical and insightful approach to analyzing biological data has empowered countless learners to engage deeply with ecological research using robust statistical frameworks. Internationally, his work has received wide acclaim. He had awarded the Canadian government postdoctoral fellowship during his tenure at the Pacific Biological Station at Nanaimo, British Columbia, and earlier received the East-West Center Scholarship funded by US federal government. His global impact was further recognized through invitation as a visiting scientist at the International Institute of Ecology in Brazil and the National Taiwan Ocean University in Kowloon, Taiwan. Rao was honored with the Teacher of the Year award by the Indian National Science Academy, a prestigious recognition of his unwavering commitment to mentoring and academic excellence. With over 65 publications and having guided 10 PhD and 12 MPhil, his legacy continued to illuminate the academic and scientific community. There is much more that could be said about Professor Rao, but in the interest of time, I will pause here. It is how my privilege to invite Professor T.R. Rao to deliver his lecture and share his profound insight on the test of hypothesis. Over to you, sir.
Thank you, Savinder. Hello, everybody. So you have seen me before. So I'm turning off my video and start the projection. Are you able to see my screen? Hello? Are you able to see this?
Yes, sir.
Oh, very good. Very good. Okay. Okay. The topic we are going to discuss today is hypothesis testing. This is of course fundamental because why else do we do statistics? We have as biologists, maybe other some subjects, we have a hypothesis to test, and the statistics comes to our aid and provides the right kind of tools to test our hypothesis. Basically, the scientific method, of course, is you start with observation. That observation leads to setting up an hypothesis or asking some kind of a question of how, why, or whatever. And then you set up an experiment with proper experimental design, conduct the experiment, obtain the result, subject these results to a statistical analysis, and reach the conclusions. Okay. So, having finished the observations, we are now see how to go about doing the hypothesis testing. Let us take a fictitious example. But before that, let us quickly review what we meant by hypothesis. It's an explanation in trial. Okay, you try it, and if it proves to be right, then the explanation becomes a truth. So, it two requirements: testability and quantifiability. I'm showing you a few examples here. Now, those of you who are watching, you should be able to quickly answer me out of these, which are the ones that are testable and which are the ones that are not testable. Just tell me which are not easily testable. If you quickly give answers, yes, fine, because otherwise we waste time. So anyway, I show you the answers. So these three are not easily testable, right? Because look at bank went bankrupt because of a mismatched Kundalini. Now, this is something, it's based on beliefs, superstitions. There is nothing you can prove in a scientific basis. Now, again, about the female applicant being having a better chance of getting a job, again, one would say beauty is in the beholder's eye. It's such a personal attribute. So, how do we quantify in an objective way? No way, right? So these are some of the things which are amenable to, not amenable to statistical analysis. So now I will start with a simple example. It is fictitious, but not untrue, not very far from truth. So pharmacologists, phytochemists going to Western Ghats exploring to see if they can find some medicinally useful plants. Okay, just a more. You have
Participants
problem?
are requested to switch on or switch off their microphone.
Yeah, that helps. So that is their observation. Now, based on that, the scientist sets up a hypothesis. What is the hypothesis? The leaf extracts of this plant could help in reducing blood glucose levels. Okay. something of great clinical importance, pharmacological importance. So now, what do you do? A kind of an experiment now. You take 20 diabetic patients who are willing to participate in this experiment, and so human volunteers. Let us say that their average values of glucose, blood glucose, based on conversion from HB1AC, gives an average value of 180. Okay. As you know, the normal value should be 100 or below. So, no, but they have not been taking any medicines. That's ideal. Now, so you divide them into two groups randomly. One group receives the medicinal pill containing the leaf extract. The other group doesn't, but it receives a placebo to give the feeling, psychological feeling to the patient that he is receiving the medicine. Okay, that's what placebo means. So after given certain amount of experimental period, now you test these values again, their glucose values. Now, after 30 days, the mean glucose value comes to 172 in the treated group. That means the group that received the medicated pill, and 180 more or less in the same control group. So, now how do we interpret this one? There is definitely a reduction from 180 to 172 in the glucose value. So we conclude that this plant chemical is capable of lowering the blood glucose levels. If this is true, now we have a bonanza of some new medication that you could um, sort of commercialize it. But the question we ask is this: are we sure that this does this job? You say, how? Why are you asking that question? We showed you that there is a reduction of 8 units of glucose loss, depletion, right? So, but we say, look, if you look at the percentage, it's just 5%. Then you say, yeah, sure, 5% is good. Why not? But we say, look, isn't it possible? Observe this question carefully. Isn't it possible that this small difference of 5% could have arisen just sheer chance alone, not due to the effect of the medicine, the leaf extract? Many things happen by chance, which you didn't expect, right? In life, you say, oh, just luck, it happened. Just by chance, I got it. So this means life is full of probabilities. In biology, many things are probabilistic. So we are asking this question: isn't it possible, isn't it probable that this small difference arose only due to chance, but not due to the active chemical in the leaf extract? Okay? So, how do we show? This question, which is a very, very important question in statistics, has been addressed by none other than Ronald Fisher. Okay, he is the father of modern biological statistics. So he addressed this question and came up with a testing procedure which is called null hypothesis test significance testing, popularly abbreviated NHST. Okay, these Fisher, along with Nyman and Pearson, proposed this. And what does it say? Read this carefully. So it says how much it differs from the true value. Okay, so what is the probability that the value you got that truly represents the population value, which is that it is really works? Okay, so this P is something of great importance. We will discuss about that later. So first of all, learn how to set up a hypothesis. You provide, say, observation and say, call that as a hypothesis. Let us say 4 examples. Now, when you propose a hypothesis, in statistics requires that you propose the opposite of what you expect. That is called null hypothesis. Null means no. See, basically what you're saying is, if you think, say, that started with the belief extract has an effect, okay, you start with the hypothesis that it doesn't have an effect. What statistics does, it just lets you reject that hypothesis if there is significant. That means now you are saying, I will take the opposite of this. If I reject, that means my hypothesis is proved that the leaf extract has some active medication, right? So that is called null hypothesis. So let us see how the null hypothesis looks for these observations on the left side. So this you show in terms of a symbolic presentation like this. The mean value, or whatever that emotional stress you measure, of the females is the same as the of the males. Treated versus controls. It is the same. When you disprove this, when you reject this hypothesis, you're showing that it is there. So in these examples, I hope you are recognizing the fact that null hypothesis means we say that there is no association or significance. Then we set out with statistical analysis to prove that hypothesis is rejected, the null hypothesis, and then come to the conclusion. Okay. So another terminology you should know. Now, when you are comparing, let us say, two groups, men and women, okay, W and M, that is the hypothesis that cholesterol levels are the same in both males and females. You could also put the hypothesis this way, that the difference in the mean values is zero. Same thing as equal to. Now, each normal distribution, probably somebody has discussed at length the properties of normal distribution. So here you see that normal distribution spreads on both sides, extending infinity. It doesn't touch zeros. These are called the tails. So each normal distribution has a tail on one side and a tail on the other side. So these are called two tails. So your hypothesis could be two-tailed. What do we mean by this? Two-tailed hypothesis means that whether the male is more or the female is more doesn't matter. We are simply saying it is different. So the conclusion could come out the either way, that females are more or males are more in terms of cholesterol levels. This is a two-tailed hypothesis. But suppose you have some knowledge that the females have generally higher levels of cholesterol, you could propose your hypothesis as a one-tailed hypothesis and say this way, null hypothesis, that you are saying that the cholesterol levels of mean cholesterol levels of women are generally lower or equal to men's. This, it's only one-sided hypothesis because it's not looking at the other possibility, and hence it is called a one-tailed hypothesis. That means it's looking at, say, lower than this. So it might be looking at only left side of the tail, not the right side of the tail. So that's called one-tailed hypothesis. You might ask, what does it make a difference? Does it matter? Yes, it does matter. Later, we'll come to that. When we read the probability of the hypothesis being right, that is looking at only one side of this thing, whereas the other one is looking at both sides of the curve, and hence probabilities might have to be halved. All right. So, is it slight difference between statistical hypothesis and the scientific hypothesis? statistical, now suppose you say A soil plants produce more seeds than B, you statistics only tells you the difference in these two is significant or not. It doesn't establish the cause for this difference. The statistics stops there and promotes you or persuades you to go ahead and test since there is a difference. Why? Okay, so we ask this question, why is the seed number different? Now you hypothesis. So you might say soil A has higher nutrient levels than soil B. That helps to produce plants with higher seed content. Then you can test by experiment where you look at nitrates and phosphate levels and put them in different growing chambers levels and then try to grow these plants. It'll take many years to come to the seed production, but that is the experimental approach in a scientific method. Statistical method only tells you if the differences are okay. Now, this is very important concept. Now, try to follow very carefully. We are trying to estimate the population parameters based on our sample parameters, right? Let us say that normal human pulse rate or heart rate is 72. Okay. Let us say somebody from Mars comes to check. He doesn't know what the truth is. He doesn't know that this is average mean value is 72. He measures with some advanced laser technology. He just points out and it tells the heart rate of the person he encounters. So he will set up an hypothesis, something like, I don't know about it is going to be, let us say I set it up as 60. Okay. Now he will collect a sample of individuals, analyze them, and see if this estimate is close to the truth, which is 72. But he doesn't know the truth. Right? He doesn't know it is 72. He has an estimate and hopes that it is a true representation of the population mean. In doing so, you might commit some errors because you don't know the real truth. You have only a sample mean, and based on you're making a conclusion which may be right or which might be wrong. Correct? So he might be committing some errors in doing that. So what are those errors? What kind of errors are these? So now follow this carefully. Let us say drug A has a significant effect on serum cholesterol. That is a truth. Okay. Now, four types of conclusions can arise out of this hypothesis testing when you finish your experiment and got the results and try to reach the conclusions. One conclusion is that the study finds that the effect is there, significant effect, which is true. The drug has real effect, and you proved that it has an effect. Good. Two, drug has a real effect, but you were concluded that it does. This is probably because your sample size probably was small or your sample was not random, you concluded that it doesn't have an effect. Three, the drug has no effect, in honestly, but your study somehow reached a conclusion that it does have an effect. Again, sample effect. Okay, when the drug really has no effect, you showed that it has an effect. Okay, the drug has no effect, that the study has proved that it has an effect. Okay, so four possibilities. Okay, where do we make the errors? The drug big effect is there, you reach the same conclusion, this is correct. Drug effect is there, you reach the conclusion that it is not. Second, drug effect is not there, you also concluded it's not there. Fine. Here, there is no drug effect, but you conclude it is there. So, in these two cases, you reach the correct conclusion based on your sample. What your sample estimated and what the conclusion reached, Luckily, by chance or whatever it is, it proved to be exactly the same case in the population. You reach the correct conclusions. How about the other two? In number two, it has a real effect, but you conclude it doesn't have an effect. That was an error, right? When it is there, your sample made you conclude that it doesn't have an effect. This also is an error because when there is no effect, you conclude, hey, there is an effect. These are the two errors in any study. So, here we have rejected a true null hypothesis. When there is an effect, you said there is no effect. You rejected that hypothesis. Here, we have accepted a false null hypothesis. When there is no effect at all, you accepted the false null hypothesis that it has an effect. These are the two errors we commit in our statistical testing procedures because ours is only a random sample. We are only hoping that it is a true estimate of the population values. Population values we don't know. If we knew, there is no research involved. You straight away, you don't have to do any sampling. You have the right values. If these Martians guys knew the value is 72 of the, he didn't have to do any random sampling and try to estimate. He'll simply say, on this planet, these beings whom we call humans, they have a pulse rate of 72. So, in any biological experiment, you don't know the truth. You are trying to estimate it through a random sample. So, and in that process, you are likely to make two mistakes. These are the two mistakes. We'll give names for them. The error of rejecting a true null hypothesis, that is number two, is a, and there's other is this is called type 1 error. Not because I showed this first or it came first, it is always called type 1. So when somebody says in any conference, any meeting, or in a paper, this is a type 1 error, you immediately realize he's talking about error of rejecting a true null hypothesis. Okay. The second one, error of accepting a false null hypothesis, you guessed it, it's called type 2 error. And they have Greek alphabets. Type 1 error is always designated as alpha, and type 2 error is always designated as beta. So far, okay? I want to make sure that this is perfectly understood. If you have any questions, feel free to ask me. Okay, we'll proceed. And now we are going to test it with an example, this concept. First, we'll start with a judiciary example, just for fun. Okay, the accused is brought to the court, okay, for inquiry. And then after all these things are over, arguments, pro and, prosecution, defense, etc., the court reaches a conclusion and gives the sentence. But in judiciary system, any person, accused person, is considered not guilty until proven guilty. Okay? It grants. I don't think there is anywhere a system in the world which doesn't say so. You are considered innocent until proven guilty. So that's our null hypothesis. So this is the system where the jury is appointed. Okay? So the jury deliberates, looking at or hearing the arguments by prosecution, the defense attorneys, and reaches a conclusion. What is conclusion they can reach? Two possibilities: guilty or not guilty, right? Now, so we are going to look at the possibilities against these two, against the truth, whether it's true or false. Now, four possibilities arise. Here, these two are correct verdict. This is not, accused person is not guilty. And jury also reached the same conclusion. So that's correct verdict. Here, the accused person is not guilty, this is true. And here also, they have reached the conclusion. So these two against the other two, those are wrong verdicts. When it is true, you conclude he is guilty. When he is not guilty, you conclude as guilty. Okay, so these are the two blunders, errors you could make. The error of rejecting a true null hypothesis, type 1 error, and type 2 error is error of accepting a false null hypothesis. I'm going to reinforce this with a clinical example. Right? Okay. Let us take a COVID one. Okay. But you go to a COVID testing center only when you suspect you have a cold, no, COVID, right? COVID-19. That means that the null hypothesis for us is patient has COVID. He has the virus. Now, the testing device or apparatus, there are two possibilities. Since you go only with the hypothesis, it could be true or not true. If it is true, that means he does have COVID. If it is false, he doesn't have it. So the test is taken, results could become positive or negative. Okay, depending on the sensitivity of the machine or the tools. Okay, so now again, four possibilities. Just read this and absorb it. Now, can you tell me where type 1 error is committed and where type 2 is committed? I will call, let's say, left top A, right is B, bottom C, and then D. Which one? This is A, B, C, D. Now tell me, type 1 error? Come on, any of the participants, quick.
Participants are requested to answer either chat box or unmute yourself.
Yeah, unmute and say something that to show that you understood this very important concept. Oh, well, I mean, you can't wait because the time is limited. So we'll show the results. That's type 1 error. The test came out as negative, that he doesn't have. That is type 1 error, rejecting a true null hypothesis. That is type 2 error. When he didn't have COVID, your test came out positive. You can imagine what kind of trauma he will go through when he doesn't have, test says you have it, then he goes home, his wife is worried, and really traumatic situation. But it is the machine, the test that goofed. Okay. So these are the two types of errors. So in this case, it was a false alarm. Okay? When he doesn't have, the test came out positive. So it's a false alarm. When the patient doesn't have, you came out with the statement it is he does have. What will be the opposite of that? What would you call this one? Similar to like this one. Anybody can make a suggestion on what we'll label this? Type 1 error? Come on, quick. Oh, come on. Think of some suggestions, ideas, some terminology. See, this is a problem with online classes. For all
Yes,
we know, you may not be there, none of you, or simply you're not following. Offline class, I can see your faces and see if you understood or not. But unfortunately, time is limited. I hope you are able to follow. Otherwise, your teachers will give some exercise and by which you can try to follow. Okay, but this we call it as failed alarms. That means when patient had the COVID, your test gave negative, and it should have rung the alarm, then saying that no, this guy has COVID. It didn't do it. The alarm should have come off, but it didn't. So it's a failed alarm, whereas that's a false alarm.
so there was a message on the chat box, untrue alarm.
I wanted it something to match with false alarms.
Okay, false. Okay.
Anyway,
Actually, I was thinking what terms we can give, but I was
uh,
unable to give that any term to this particular failed alarm.
yeah. No, some people will come with the right answer, but not the right term to match with false alarms.
Yes, sir.
Well, you see, if there is a smoke, the smoke alarm should start ringing so that it will be, alarm to everybody. If it didn't, the alarm failed, they will say. It should
Yes.
have, right, right. So is there some humor for you? So which one is type 1 error? Which one is type 2 error? Quickly. That's too late.
Sir, can I?
Yeah.
Sir,
But I want from the participant.
Yeah, one of the participants raised, I think, their voice. So, Miss, you wanted to say, which one is type
sir,
1 error?
according to me, B1 is the type 1 error.
B is type 1 error. You're rejecting a
Yeah.
true null hypothesis. And A is, of
Yes,
course, obviously the
actually.
objective. You're right. Good. Okay. All right. So now the other one is that many of these tests talk about sensitivity of the test and the specificity of the test. If okay, patient should test positive if he has COVID-19. That is called sensitive. You ask how sensitive is the test. You say 95% probability, etc. So it must test positive if the guy truly has it. And specificity refers to he should not test positive if he doesn't have it. That means it should come out negative if the patient is healthy. Okay? So these are two important concepts. Now see, where does specificity and sensitivity come here in this uh, grid? Anyway, I'm supposed to give two lectures today, so I have to rush, otherwise, Savindra will keep saying, "Sir, can you finish it? Can you finish, please, please?" Savindra, I assume that there is no lecture immediately following, that it is only a lunch break.
Yes, sir. Yes, sir.
So,
We
which means
have.
if necessary, I can keep them starved for a few more minutes.
Yes, sir. Yes, sir.
Okay. All right. Okay. So, um, you can see where that is sensitivity, because it should come out positive when the patient has it, right? That's sensitive. And this is specificity. It should come out negative if he doesn't have it. So these are two terms that are used in testing procedures in many clinical applications. So this is quickly a numerical example. So now this machine, the test has a 95% chance of probability of detecting. That is sensitivity. That means in 95% of the cases, it will correctly show if he has the disease. Okay? And 90% chance of correctly indicating when the disease is absent and it says negative. Now look at the probability tree. when this randomly anybody who can goes, yes, 8% probability of having the disease that he doesn't have. Now the testing, the test what it does, it shows it's either positive or negative. This is 95% sensitive, so 0.95 comes on the top, and it shows negative 0.5 of the time. And same thing here. Because the sensitivity is 90, specificity is 90%, so 10% will test positive and he doesn't have. You got it? So now look at the multiply the probabilities. Sorry. So he has the disease and test came out positive, so that is true positive. The disease, he has the disease, test came out negative, so that's a false negative. This guy, he tests positive, okay, but he doesn't have, so it's a false positive. He doesn't have the disease, test also comes negative, that's a true negative. So you can check quickly the probability that a person coming from this population will test positive is due to two reasons. One is true positive, the other one is false positive. So that means if 1,000 people from this population went for checking, okay, 168 will test positive, out of which 76 will be true positives, okay, and 92 will be false positives. These false positives will go home very worried and this kind of thing, and probably they will go to hospital and get it tested again, and that will come up negative. Okay, so before we go to the next concept, we quickly go through the properties of the normal curve, which you might have gone through in an earlier lecture by somebody else, but I just review. Basically, the important property of normal distribution is the area is specified by an equation. Okay, so now we don't go through the equation, but I just show you the population mean mu plus one standard deviation on each side will cover 68 point something of the total curve area. Okay. One standard deviation on each side of the mean. If you take two standard deviations on the mean, it will cover now 95.46% of the area. But when we say area, because we're looking at the graph, the curve, but if you look at the samples and population, all those things, what we are saying is, if you took 100, say, patients' values, okay, 95 of them, they will lie in this zone of mu plus or minus 2 standard deviations. Only 5 will be away from that, 5 out of the 100. But what if we go to 3 standard deviations on each side? Now, practically the entire curve is covered, 99.72%. This means in a sample of 1,000, okay, only 3 or 4 will be out of the range here, which is mu plus or minus 3 standard. Now, if you are thinking that if we extend to 4 standard deviations on each side, we will not touch 0 or 100% on this side. That is the property of normal distribution, that the tails will never touch the extreme values, 0 or 100. Theoretically, if you want to say what will happen if you have 4 standard deviations, it might go to 99.85 or something like that. It will never go. So let us take only the 95%. That means the other 5% are not within our acceptance region or the major values. This is like saying, I am willing to say that I allow for 5% error of rejecting a true null hypothesis. Okay, so this means if these are the critical values within which our acceptance, the away from that will be the rejection regions. Since alpha is 0.5, these two will be half alpha, which is 0.25, 0.025, 0.25. Okay? These are called the critical values. This concept is important for what I am going to discuss. So, that is the area in which our hypothesis is acceptable, mu plus or minus 2 standard deviations. Away from it on either side, we reject the hypothesis. If you increase it to 0.1, that is only one chance out of 100. Now you can see that the band has widened, mu plus or minus 3 standard deviations. Our acceptance region has widened, and rejection regions on sides have come down to 1/4 of total, something like what 0.125 or something. Okay, so this concept is important. Now we talked about type 1 error and type 2 error. How much type 1 error can we allow in testing our results? Remember what type 1 error means, then you will understand. We are saying, what is the probability that my hypothesis is wrong? Is it 5% allowed true rejection of a true null hypothesis? Or what is the level? Let us say alpha, we can set it up at 0.5. That means you're willing to let go 5 chances out of 100. Fine. Is this alpha fixed by the investigator? More or less. There is a lot of theory about it, but basically it is fixed by the investigator based on the available norms throughout the world. It is fixed at 0.5. But you can fix it at 0.1 and give justification. But the problem is now, what is type 2 error? How much type 2 error should we allow? This we don't know, because type 2 error is accepting a false null hypothesis. If we don't know what is true null hypothesis, how would we know what is false null hypothesis? We don't have at hand. If 72 is not the correct one, the average heartbeat of a human being, what is the correct one? Do we have any idea? We don't know. So we generally do not have any idea about what beta error should be or could be. Okay? But we can guesstimate how it is going to be depending upon the extent of type 1 error, which I will show in the next couple of graphs. And these graphs will also illustrate the relation between these two errors. Okay, but for theory sake, I am presenting an alternative hypothesis so that we can evaluate the type 2 error. Okay, this is our original hypothesis. I call it HO, right? The base hypothesis, that the mean is 50. And we defined the acceptance region because this is 95%, the alpha set at 0.5. And the rejection region we identified. Now, let us say that we have the alternate hypothesis where we have a mean of 42, not 30, but 42. This alternate hypothesis, which we don't know, but theory's sake, to explain the theory, I am proposing an alternate hypothesis that the mean is 42. Okay. So now something interesting happens. I kept the standard deviation the same just for the convenience for both, okay, which is 4. Okay. Now, see what happens. Part of this alternate curve with its mean of 42 is falling into the acceptance region of this hypothesis, our original hypothesis, HO, okay? Which part? That part. This part of the curve of A, that is our alternate hypothesis, comes into the acceptance region, because this is the acceptance region of curve A, our original curve. What does this mean? this is a false null hypothesis, okay? And we are accepting these values because they are coming to the acceptance region. So you are accepting a false null hypothesis because you started out with the mu is 30, and now you are accepting for these values, which is 42, you are committing an error. And that error is beta error, type 2 error. Because type 2 error means that you're accepting false null hypothesis, right, in their studies. But there are other methods. Later we will come on. I won't come in this, but in this course, somebody might discuss how to sort of come up with their estimate of beta error. That's involves statistic. Okay. But at least you understood now what happened. Now just change it now, type 1 error to not 0.5 but 0.1. Okay, allowing for only 1% error. So now see carefully what happens. What happened now? A larger area of alternate hypothesis falling into our acceptance region of the original hypothesis. Okay? And watch that 1 minus beta also, because if this is beta, this area, this is 1 minus beta. Now I put these two together so you can appreciate. What's the big difference between these two? One is set at 0.5, the other one is set at 0.1. Now, quickly you should have said the difference is that a larger proportion of alternate hypothesis values come into acceptance region when we decrease alpha to 0.1. That means the beta error increases when you set it at, compared to this, it's much larger beta value, you are taking in more false acceptance values. That is the relation. This means now, obviously, these two are related in an inverse way. The more you are, the less level you put alpha, okay, the more will be the beta error possibility. Okay. So now what I want to show, I hope you understood. This means now if you set at 0.1 instead of 0.5, there is a greater likelihood that you'll be committing more of beta errors. Okay? Remember that. That's why you have to be cautious. You should not say, oh, I want to be very stringent and want to set up alpha only at 0.1, which many investigators do when in clinical studies, where human life is very valuable and they can't afford to miss 5 errors out of 100. One is okay out of 100. But in that process, they might increase beta error. Now, so we know that these are inversely related. The greater is the the alpha set, greater means of course lower is the one, the greater is the beta error. Now, I want you to observe this gray shaded area signifies.
Sir, it's very interesting because even I am finding it very fascinating. Like I think this is the area showing that if our values fall in this region, we will reject our null hypothesis and will say that both the population are having significant difference. Am I right,
See,
sir?
listen, these are accepting false null hypothesis, they are low, right?
Yes, sir.
Right. That means these are rejecting the false null hypothesis, right? If this is this piece is accepted, this is rejecting. Agreed?
Yes, sir. Yes, sir.
Right. Which means now your effort should be in your research studies to decrease this and increase more. This I 1 minus beta, which means actually you want to keep false acceptance as low as possible so that the rejection of the false null hypothesis will be higher. That's what it is true, right? You want to reject as much as possible a false null hypothesis so that you can pick up the correct hypothesis. So this is inverse relationship. So the smaller the beta error, the more that number of things falsely that you will reject. And that's why this 1 minus beta is a measure of the power of the test. Okay? That's the thing. So one should try to keep this beta error minimal so that the power of the test will increase. The smaller this is, the greater this area, which means the power is greater. How this is done in a experimental design planning is a topic for later discussions in a full course, but not here. Anyway, so this is the conceptual issues related to hypothesis testing. You choose between beta errors and alpha errors and see how to balance these two because these two are inversely related. So here is, do you know this guy who can identify quickly? Anybody? Anybody? Anybody can guess? Too bad. But this is Benjamin Franklin, whose image appears in all American currency notes. He once said something very important statement, which we can see if we can relate it to some statistical concept. He said, it's better that 100 guilty persons escape than one innocent person being punished. Let 100% real guilty people go free, scot free. But make sure that the innocent person is not found guilty and put in jail. Can we interpret this in statistical terms? Yeah, I mean, nobody told me, but I just tried this for a while and it occurred to me that it could be nicely stated like this. One should try to keep type 1 error to the minimum. That means the number who are innocent being punished to the minimum, even if it means much higher type 2 error. Even if you will leave out 100, 200 guilty persons saying that you are free to go, you are innocent. That could be allowed, but you should not allow innocent person to suffer. Okay? So this means as far as possible, you should try to keep type 1 error to the minimum. Okay? So let's take a 5-minute break.
Thank you, sir. And
Okay.
now I request all the participants to mark their attendance. And I request one more thing. When sir is asking, please try to answer, even if you have some doubt.
Even if your answer is wrong, it doesn't matter. Just answer.
Yes, sir.
Okay, let's take 5-minute break.
Yes, sir. Yes, 5 minutes break, sir.
Yeah. Okay. But responsible outcome of this please. అట్లీస్ట్ నువ్వు సువర్ణ సేవ చేస్తున్నప్పుడు కొన్ని మొహాలు చూస్తుంటారు ఎనభై మంది ఉన్నారు.
But can't you just see?
No. I mean, I can put, but you need distracting because when I'm giving a lecture to see who is present, who is not, I don't take that names. They take. Organizers are taking attendance.
But still, no.
Yeah, but I would like to
You
say,
can point out to somebody.
okay,
else.
Anita, what is the answer?
Yeah, right.
Nayanika, what is?
అలా చేయొచ్చు కదా.
Yeah, but it takes a lot of time. You see, but that's possible only in offline because there is no time limitation. Here, they gave 45 minutes, I have to finish. Yeah. Now, can they assemble?
Yes, sir. We all were enjoying.
Here already?
Yes, sir.
Okay, go. Okay, thank you. One of my vices, one of my bad habits. Okay, now we'll look at a concept called confidence intervals, then move on to conduct one test. Okay, see, our basic tenet is that we are trying to take a random sample of the population and try to estimate the population values from our sample mean. In this, we assume that our sample is random. Since it's random, it should actually give a true estimate of what the population value is. Okay? But the question we ask is this: how confident are we? Okay? Now, it's like asking, I give you an example where I run into a student who has given 12th exam. Okay? I ask him, what are you expecting in physics? Okay? He says 72% marks. Okay, I say, are you sure? Yes, he says, yeah, I'll get 72 or so. I said, are you sure? I repeat the question. Now he says, well, now that you say, I think I'll get it between 65 and 75. So this means for his estimate, he is giving some confidence limits. That means he is confident it should be definitely the marks he will get in physics will be going to be definitely between 65 and 75. That the interval that he is giving is called the confidence interval for his estimate. His estimate, which is like our sample mean, is 72. But the population mean doesn't know. He doesn't know what finally he'll get the marks. Right? So he's giving a confidence limits. Okay, I should get definitely between this and this. That is what we want to do in statistics because we are never 100% sure. Even if we say probability of 5% being wrong, that is type 1 error allowed, still you are not too sure. So we will learn how to build confidence intervals for our sample mean. Okay. So generally what we specified is two standard deviations on each side cover 95% of the values. Okay, that means now when you give this limit on each, that means two standard deviations on each side, you are saying there are 95% chance that what I am estimating is going to lie between these two limits. There is a 5% chance that they will be away from it. Okay, so okay. So instead of the population standard deviation, we replace it with our sample standard deviation. Yes, which for which we have given the reasoning earlier in my first lecture. Okay, anyway, we come to that and we bring in standard error instead of standard deviation, which is a function of the sample size. So that is the confidence interval, two standard deviations on each side. Now let us see people really misrepresent the statement. When we say with 95% confidence interval, you make a statement. Say my mean is going to lie between though and or this value and this value with 5% error, which is type 1 error. What they say generally is like this. Now what I'm doing is let us say we take 20 subsamples from the population. Okay, subsamples of 20, 40, whatever it is. For each, we determine the mean and standard deviation. So here we are showing those 20 samples with their mean, the red dot, and the standard deviation. Okay? Now, listen to this. I mean, look at the statement you say, the interpretation. there is a 95% chance that the true population mean lies within this interval. The interval defined by two standard deviations on either side. Is that okay, this statement? Hmm?
Yes, sir.
No, it's not true. You know why? This means now this statement means time the true population mean lies outside its limits. How could population mean change? Mean is a fixed value. Population mean is a fixed value. How could you say that 95% of the time it will be there and 5% of the time the population will be different? The population mean is a fixed value you are trying to estimate. So that is a wrong statement. The correct statement is like this. 9 I have calculated, my population mean should lie there. Well, I don't know what the population mean is, but it is going to lie in this. Since it's 5% chance of being wrong, this particular value, this dot, you see, it is away from my confidence interval, right? So this means there is 1% chance, 5% chance that my confidence interval does not include the true population mean. That's okay with us because we specified 0.5 error. So this means now for anything in research, any statement about the effect of something and the differences between two means everywhere, you are not 100% sure. You can only say with 95% confidence or 99% confidence. And that means 95% of the time, the what you estimated, the population mean will lie in this zone. In this zone, naturally, 19 of these things are still in your list. They gave the limits you gave. Only one deviated from it. It's okay. So this is the correct statement. Now, in this one, what happened? There are two values that deviated. This one and this one. This means now your rejection things, you have to state that 90% of the time, not 95% of the time. Then you will be right. 90% of the time, 90% of the samples, the population mean will lie in the things that I have specified. Okay? But 5% of the values, 10% of the values will lie beyond my confidence limits that I have specified. So here you cannot claim that is you are saying type 1 error of 0.5, right? All right. And we use this confidence interval formula, standard error multiplied by 1.96 and plus or minus the mean, sample mean, remember. What is this 1.96? All the time we were discussing two standard deviations on each side of the mean. Where did this 1.96 come? Anybody quickly? Huh? It should have been 2. What is this 1.96?
No idea, sir.
Huh?
No idea.
Okay, I'll tell you. You see, you remember that two standard deviations on each side of the mean cover what percentage?
95 point, sorry, 95.24 if I'm not wrong.
95 point something, right?
Yes, yes, sir.
So here we want to make it exactly 95, no decimal. So if it is 95.4 or something is two standard deviations, exactly 95% would come to 1.96. As simple as that. Got it?
Sir, can you repeat it one more time?
In the theoretical distribution, we said two standard deviations on each side cover 95.4%. Okay, exactly. Okay. That is two standard deviations. But in these statements here, we are making 95% confidence interval. We are not saying 95.4% confidence interval.
Okay, sir.
So
Okay.
from that 95.4 to bring it down to 95%, it becomes 1.96 instead of 2.
Okay, sir. Okay.
This means it's 1.96 standard deviations on both sides will give you exactly 95%.
Okay, sir.
Standard error is simply standard deviation divided by root n, which is n is sample size. Okay. If we want to be more confident, okay, we take 3 standard deviations on each side, right? Now we put 2.57. But why is this 2.57?
I think now we have taken 3 standard deviation,
Yeah. But why 2.57?
making it perfectly 99%.
Right. Yeah. Instead of the 99.72 that is there, we bring it down to 99 because we can't be making about decimal things 97.72% confident. We say either 95% confident or 95% confident. Okay. So to make it 99 exactly, this value will come down from 3 standard deviations to 2.57. Logical, right?
Yes,
So
sir.
then now when you multiply obviously with 2.57, the confidence interval will be wider. Okay, it will cover more values. So if you have 100 values, 99 will come under this the interval that you have specified. That's the idea. Okay. So I'm just showing an example how to make use of this confidence interval. Okay, so we measured the body size of Daphnia, this water flea, in the zooplankton of any freshwater pond. We have taken 120, measured their body size. Mean came to 11.2 millimeters with a standard deviation of 1.8. Okay, so we calculate standard error and then with 1.96 multiplicand, we get confidence interval of 11.2 plus or minus 0.322, which gives us 10.88 to 11.52. Now, what is the statement we make? With 95% confidence, I am stating that the true population mean body size of Daphnia is going to lie between 10.88 and 11.52. If you measured 100 of them, I will say that only 5 will be out of this range. Either it will be smaller than 10.88 or larger than 11.52. But 95 values should come under this interval. That's the statement we are making. So based on your sample, with allowing for some type 1 error of 0.501, you're able to say what the population mean is going to be. So this comes in handy when you are doing some testing procedures, because in testing, you are never 100% sure. There is another example. I'll skip this. This is same thing with a. The difference here is we have a set population value. Okay, so mu is equal to 12, but then we specify, give the null hypothesis, it should be more than, we prove it's not. The idea is the children exposed to lead, do they have lower hemoglobin levels? We take a set of data and calculate the basic parameters, come up with standard error, apply our formula to get the confidence intervals. We get the values of 10.91 to 11.29. At this stage, I'm going to give you a hint. This range, allowing for 5% error, should have covered the population mean. Did it? Even if you allow for 5% error, even if you go to 99%, did it cover? Yes or no? It's so obvious. Come on. Say no, because 10.91 to 11.29 does not include 12 population
Yes,
mean.
yes, sir.
All right. But the implication of this is, listen carefully, you can conclude now with 5% error possibility, or you can say the other way. With the 95% confidence intervals, the population hemoglobin normal value is definitely significantly less than 12, because 12 is not included in my confidence interval. So you are showing it significantly lower than 12 in children exposed to lead. Of these, you show bar diagrams like this. On each side, you show standard errors or standard deviations, but I would prefer that you plot confidence intervals. Mean plus two standard deviations minus two standard deviations. Two standard deviations. Okay. Here, two groups are being compared. All right. Yeah, tell me. In this graph, yeah. See, you can see that A and B differ in the mean values, right? If you draw a line like this, you can see that B has a higher mean value. But statistically, you have to do a t-test. A box plot, yeah. Sorry, I meant to say box plot rather than bar diagram. Sorry, it was supposed to be box plot. Okay, sorry, it was supposed to be box plot. Okay, yeah, right. Box plot. See, the investigators who publish papers generally they state what the error bars are. By the term error bars, it just means originally they are meant to be standard errors on each side. Okay, but some people just put standard error deviation.
So there is one more doubt. Like usually we plot it in such a way that the central point is depicting the median value.
It just depends on, if you're looking at the median and percentiles and all those things, it's fine. But if you're in a normal distribution, you are considering any parameter, it's better you deal with the mean, because all our statistics are centering around mean, not median.
Okay.
In a perfect situation, mean and median will be the same. But since these graphs, everything look at normal distributed parameter, like heartbeat or any of those things, we often use mean instead of median. All statistical tests, so-called normal statistical tests, use mean. The non-parametric statistics tests are there which use median. Okay? Okay. So,
Okay, sir.
uh, so we are making some statements just to tell you how confidence intervals are used for making a statement. Now, quickly, I have 10 minutes more, half an hour more. Here, I want to say how the level of confidence you get when somebody makes a statement with confidence levels. The best situation is when a pollster takes exit polls or even pre-election polls just to get public opinion about a candidate, and he comes back to the candidate and simply say, "Sir, you have a chance of getting 35 to 60% of the votes in the election." And another comes and says, "No, you are going to get exactly between 40 and 45% of votes." Whom does the candidate believe, or at least wishes to believe? The second one, because this guy is giving a more close estimate. So the candidate can decide whether it is worth contesting the election or just. The closer, the narrower the confidence interval, the more confident you become about the statement made by somebody. So when the pollster says you are definitely going to get between 40 and 45, that's more believable than somebody saying 35 to 60. Because if it is as low as 35, you might lose the election. So the idea is the lesser the interval, the narrower the interval, the more believable it becomes. Any statement, even with the parameters, even with Daphnia size, if you said it's going to lie between 11 and 11.2, wow, that is very believable. But if you say, what can we do to get narrower confidence intervals? Narrower confidence can be achieved only by changing this, correct? This one, this has name also called uncertainty. Okay, so how much you add or subtract from mean will tell the width or range of the confidence limits. 1.9 is fixed, right? So the only thing you can change is this value. The smaller this value, the narrower will be the confidence interval. Agreed? So our point is to see if we want narrower confidence intervals and people want to believe us more, we simply do this one. Either decrease the standard deviation or increase the sample size. Correct? Did you follow this?
Yes, sir.
Yeah. So in any experimental research you are doing, either for your doctorate or whatever it is, to increase the confidence thing in your statement about population values or significance, you want to make sure that it is the interval is as narrow as possible. That means you have to reduce the confidence interval, which means you can do either of these two or both. Now the question is how to reduce standard deviation. And we say, look, that is silly because standard deviation is a property, inherent property of the population. It shows heterogeneity, variation. How can we do anything about it? But we say, okay, relax. I'm not talking about the population, I'm talking about your sample. Ensure you that your sample is as homogeneous as possible. Okay? That means now, when you take a sample, let us say, of people for some opinion survey, make sure that the people are homogeneous in the sense, don't include young ones, children, juveniles, who may not have any strong opinion about political issues or whatever. Okay, don't include two different socio-economic strata. If you are going to do it in a shopping mall, fine. But if you are going out and doing in the field, don't include in the same sample people from Kotis and people from Jaggijopolis. So this is how you try to see as much homogeneity as possible in your sample. Population, you can't do anything about it. But at least you can ensure the sample you are collecting random and not too heterogeneous. That means not too much standard deviation. To give a biological example, you are taking a sample of, say, a fruit flies or some plant measuring the length of the internodal thing. Now, accidentally you create some other plant or something that's normally long or something. Your standard deviation calculation will show a large standard deviation. Then you go back and say, well, what happened? So you say, oh, these two are belong to some other variety. I accidentally included in my sample. That's why the variation has increased. So that is one thing. Now, how to increase the sample size? Because that also will narrow down these. This is a perennial problem for many investigators. What size, sample size should I take? In the conferences also, people will ask, hey, what's your sample size? Well, the thing is, for each experiment, each has its own rules, etc. But basically, If you take too large a sample, you have problems. If your sample is too small, you have a problem. Quickly, too large a sample, if it is fruit flies, if it is E. coli, no problem. You can take as many as you want to. But what if you are working on rhesus monkeys? How many can you get for a sample? 2, 3, even that is difficult, right? Think of elephants. Now, my extreme example. If says no, I for my statistical testing, I want some 10 elephants. Who will give you for any parameter? So, sample size will be a problem. Now, even if you can afford large sample sizes, you have a problem of animal rights activists getting upset with you that you are needlessly killing, sacrificing animals. So, as selecting an optimum sample size is very, very important. There are some rules and regulations on how you go about doing it, but I'm not going to go into details because it's beyond the scope of this talk. But you should consider how to take a small sample size. You see, I just illustrate. See, I tried as an exercise 3 sample sizes 20, 120, 300. Okay, see what happens. Confidence interval narrows down, right? Which means now anything beyond that range, you are going to reject the hypothesis. That means as you increase the small sample size, huh, the any small effect will become significant because it becomes very easy to reject because you gave a very small window. And beyond that, you want to reject. So the danger of selecting large sample sizes, just because you can afford to have, is that even silly small effects will become statistically significant. By the same logic, at the other extreme, if your sample size are very small, you might miss some significant effects because you're waiting for a big difference to become statistically significant. But there might be differences which are small, but yet statistically significant, biologically meaningful. So you have to select optimum sample sizes. There are some formulae and all kinds of things for calculating the sample sizes that you would require. As I said, and a full course, somebody will deliver these kinds of things. So you can see the difference. As confidence interval, how it keeps coming down with increasing sample size. Okay, we'll just complete this lecture with testing. Use our knowledge to test something, okay? And a real test. Okay, when you have a specific hypothesis, you can test it. Sometimes you have a specific, readily available hypothesis. Like, look at this product, multivitamin tablets. It specifies that the zinc amount is 10 milligrams. You can test it. You can take samples of 20 of these tablets, 20 different strips, and take one tablet from each. Get the zinc analyzed at testing lab. You have a bunch of values. You can test the hypothesis that value is 10 milligrams, right? You can collect the data, calculate standard deviation confidence intervals. That confidence intervals has to include 10. Then you say, yes, okay. But is not within that confidence interval, allowing for 5% error, you are saying the amount is not 10 milligrams. Okay? This one states the amount of chocolate, total weight is 137 grams. It should have been G, not mg. You can test this. Take 10 of these samples, check the weights on a balance in your lab. Okay, so you have a set of data of 10 values. And of course, you can sacrifice these 10 candy bars after weighing them. You can distribute to all the lab mates. Okay, or allow the boss to take all the 10 home. Okay, so here is your hypothesis that you can test. Now, see, in this kind of a hypothesis, you can set up. Now, I'm going to show a specific test. The other way that you can test a hypothesis when there is something that's already there due to generalizations, physiological or whatever it is, such as body temperature of adult humans, 37.4, 37.6, that's fixed value, so you can test it. Average heart rate of young adults, systolic blood pressure of healthy adults, these are generally assumed to be fixed values against which you can test what is existing. Okay, well, just for fun, I'm going to test an existing hypothesis, which says the classic potato chips bag contains 100 grams net weight. Is it true? You want to test. Why do you want to test? Suppose this guy is putting only 97 grams instead of 100. You generally don't weigh. You don't have a balance, nor do you care. If you have few chips missing, you won't know. But suppose this guy produces some 1 million of these bags and each he saves 3 grams. See how much profit he's making without your knowledge. So you want to investigate if these guys are cheating you. So it's a statistical bent of mind. When with the knowledge you gain from T.R. Rao's lecture, you simply say, okay, I'm going to the market, collect randomly 10 bags of this and weigh them, okay, and prepare a data set. Hypothesis to be tested, 100 grams, collected 10 bags, weighed them, and the average mean weight of the sample came to 97. So at this stage, there is suspicion that you have been short-drifted for 3 grams. We ask this question. Should this hypothesis be one-tailed or two-tailed? Just, it's so simple, I should pause more than this. You see, it should be one-tailed only because you don't complain if instead of 100, the average sample weight comes to 104. You're happy, right? You got more than what the manufacturer says randomly. You don't complain. You're worried that the customer might be cheated only when it is less than 100 claimed. So it must generally done as a one-tail test, but in this, of course, I'm showing as a two-tail test. Okay, so we take samples. Quickly, I'm showing the data. You collect, mean comes to 97, standard deviation 3, and you calculate standard error. Okay, and here we assume, say, 5% error. Okay, so now we want to calculate some parameter that will allow us to reject if the type 1 error P is less than 0.5. Because P, that limit we set is 95, right? That means 0.5 alpha. That if it is less than that, that means with rejection possibility. How to calculate this P value? There is what is called student's t-test. Most commonly used one, and many novices also know about this. This is the basis because these two values show normal distribution, and T is simply your sample mean minus the population mean divided by standard. And this is called student's t-test. Who is this student? Well, a guy, scientist who published papers with a pseudonym of student. He didn't publish with his own name for reasons. He was working for a brewery which makes wines and beer and all that. And he was a good statistician. He got training from Fisher and other people. So he developed this test. But the company rules require that they cannot publish any company data even if it is statistical. So coolly, he published a lot of papers under the pseudonym of student. And this one particular one, t-test, has been widely accepted, and he gets the credit for this. Okay, so we do the t-test and find the value. Okay, this is our sample mean. Okay, and this is population mean expected what is supposed to be. Standard error, we get a t-value 3.46. This value has to be checked in a t-table. That will tell whether the p-value comes to 0.5 or more or less. That we do go to the t-table. This t-table shows values for both one-tailed test and two-tailed test. And the degrees of freedom are generally your sample size minus 1. So in our sample, it was 12, so degrees of freedom is 11. Against 11, you go and see where your value comes in this, okay, grid. And then that will tell you whether what the p-value would be, okay, to show you. Okay, we choose two-tailed tests as the red arrow shows. Okay, our sample size was somewhere here. Okay, and now go through this. Okay, we keep going to and see where our value comes, the t value. Somewhere there, because I think our value was something there like that. So then from that you go up. Sorry. So then take it up there to read the exact probability. The probability falls between 0.5 and 0.2. The p-value comes to around 0.04 based on your t-value. Now 0.4 is less than 0.5, right? So feel free to reject the hypothesis, right? So we go a golden rule. If the p-value, t-value gives you a p-value of 0.5 or less, reject the hypothesis. If not, don't reject. So, but we can test this with confidence intervals also. This is the last, I'll just finish in 5 minutes. So here we can get the confidence intervals. I think, so I took the confidence interval, t-value is the same thing, or the other one, which is our regular formula. Now, systolic blood pressure, 15 patients, mean was 112. Our population mean is supposed to be 120, standard deviation 8.2. We calculate the confidence intervals at 5% being wrong. Type 1 error, 0.05. It gives us a confidence interval of 107.8 and 116.2. Carefully look at this. This is the thing in which our population mean should be there, allowing for 5% error. Population should be, the systolic value should be between 108, let's say, and 116. But it is not. The actual population value is 120. Right? So we reject the null hypothesis that it is 120. Because if it is within the confidence limits, if it came, then we would have said yes. But since it's outside the confidence limits, we say that is not true. The population value should not be 120, but something else. Obviously, the range does not include, it must be lower than that. Our mean value is 112. Right? So significantly less than 120. So we test this way. Okay. Since the confidence interval does not include the mean, we reject the null hypothesis, which is the same as t-test. Okay, general symbol, the symbolic thing is to call if it is 0.5, okay, the value comes out after doing your t-test, we call that the difference is significant and put a 1 asterisk. If it is even so high t-value that p-value comes to less than 0.501, we say highly significant and put 2 dots, 2 asterisks. Traditional. But some people question this and saying, if it is significant, it is significant. What is the need to say highly significant? I mean, either you are married or not married. You can't say I'm highly married. So you can, once it is significant, it is significant. Doesn't matter whether it is highly significant or so significant. So, but some in the tradition continues. If it is less than 0.1, you write highly significant. If it is less than 0.5 only, you will say significant. And with these asterisks put down there, the reader will immediately know you're talking about 0.5 level, not 0.1 level. Okay? So when you reach this conclusion, this is how you report in the paper, research paper. That's for our example. So we report, submit a report saying the mean net weight of potato chips bag is significantly less than 100 grams. P0 less than 0.5. So students t-test. That's how in a printed publication it will come. If it is more than 0.5, you cannot reject the null hypothesis. This means now follow this logic or statistical peculiarity. If it is less than 0.5, you reject. But if it is 0.5 more, you cannot say I accept. There is no such thing as accepting. Either you reject or not reject. So if it is more than 0.5, simply we cannot reject the null hypothesis. Why can't you? We don't know, because maybe if you took a larger sample, perhaps the P level would have come below 0.5. We don't know. With the sample size you have taken, the value came to more than 0.5. So you're not able to reject the hypothesis. Something silver is happening in judicial system. However, number of movies you see or court cases you go and listen to, the judge will never say he's innocent. Neither jury nor judge will proclaim he as not guilty. He will not say innocent. You might argue saying, yeah, aren't they both same? If you are not guilty, you are not innocent. No, it's a safety valve to say not guilty. Now, I just show the final 1 minute the comparison between these two. We said it is not significant because it is more than 0.5, but in your own mind you say, why is it not significant? I expected the significance. I know this biologically is very important. Then you might simply say, what if I increase the sample size? Go back and repeat the experiment, but with twice the amount of sample. Lo and behold, it might come down below 0.5. So you have the provision by saying not rejected that you can probably do something, maybe whatever is desired, to bring it back. But if you say already you accepted it, there is no further discussion on that. Same thing in judiciary. If you say it's not guilty, okay, that means you are leaving the possibility that the police might come up with more evidence. It's like larger sample size. They might come up with more evidence to show that he is guilty. So they will go and collect more information and take him to court again. And based on that, that P might come down below. And based on that, that P might come down below 0.5. And then he knows that he's guilty. They'll simply never, I don't know, many movies also I've seen, they will proclaim the accused is not guilty. Okay? So see these parallels in statements we make, because ultimately they're both related to probabilities. Statistics is all about probabilities. So these are the things that it will depend upon. And this P is suggested by Fisher, cutoff point. But there is a lot of discussion, controversy about why 0.5. Why not 0.6 as a cutoff point? Why not 0.1 or what 0.3? What is so sacrosanct about this value? Okay. Um, so then there's a lot of controversy still not decided, but the tradition continues. Rejection level 0.5 or less. Okay. But I don't want to go into this detail, which is not necessary, but how Fisher went about suggesting 0.5. So I'll stop here. And if you have any questions.
Thank you so much, sir, for clearing many doubts. Even I am teaching this paper since last 2-3 years, so many years. But yes, there were some things which I was missing, and I hope many of the faculty members have also learned some new things, and all our participants who are students will start taking interest in this subject, sir. So there are few questions.
Yeah, sure.
One common question is that when stats can tell us that is there any difference or not, but we have to find out ourselves that from where this difference is coming out. Then what is the role of the statistics?
Statistics usually first shows there is a difference. If the statistics shows there is no difference, why would you look for reasons for the difference?
Okay, sir.
Right? It has no meaning. If drugs A and B are exactly the same, there is no difference. Would you still go and investigate which is better?
Okay, sir.
Right? So we simply say that only when you feel statistically there is a difference, you do conduct an experiment.
Okay. Sir, one more question is that in the first half of your lecture, you mentioned that there are two tails, but when we are making any hypothesis, like if like girls will perform better than boys, so we generally call it two-way hypothesis or two-tail hypothesis.
Well,
Like,
it depends. You see, if your aim is to show that boys and girls differ,
yes, sir.
it doesn't matter who is greater, who is less. Then it's a two-tailed. Okay? But if you're chauvinistic and simply say, no, males are smarter than boys or something, you're proposing a one-tailed hypothesis.
Sir, one of the participants, Adil Asraf, can't ask.
He has raised his hand. I probably like to.
Hello.
Yeah.
Yeah, good afternoon, sir. Thank you so much for such a wonderful presentation. I mean, it has cleared so many doubts. I just wanted to ask the source of this T table test. Like, how do we have standardized this T table, and based on what, like, these values we check from the T table, and we say that our data is significant or not significant, or like our hypothesis is rejected. So, what is the source of this table?
You see, what it tells us, based on your calculations of your sample, it tells you the probability of you being wrong. It doesn't tell you probability of you being right. It tells you the probability of being wrong, then based on that you make a decision. If the probability of being wrong is only 2%, chalo, we simply say I definitely make a statement that these two are different. So that T table helps you to decide a final conclusion based on your data. Otherwise, you have a T value. What does the T value tell you? Nothing. But it helps you to find a P value, the alpha error value. If you set out at 0.5, then why would you deviate from that? I want to see that if it is less than 0.5 only, I reject the hypothesis. And your data will help to see where exactly is the t-value should come in order for you the p-value to be lower than 0.5. So yeah.
Thank you, sir. Thank you, sir. That's all I wanted to ask. Yeah.
Sir, I have also have the similar kind of doubt. Like we are using the pre-made table, like T table, chi-square table, but is there any set formula that if we don't have these tables, so can we also generate such kind of value so that we can?
Yeah, actually, that's a good question. But generally, these are involving a lot of algebra to come up with these T tables. Somebody must have worked about how these things come and finally prepared a table for different values of degrees of freedom, okay, and different probabilities. Now, if you want to develop on your own, in other words, in a primitive civilization, you don't know about T tables, you have to do all by yourself by using some complicated algebra. So, I mean, if it is really theoretical, you want to know, you will go to statistics department and look at one of those big statistical textbooks. They'll be giving all the derivations for T tests and F tests and all those things. Sometimes, in my course done at ISR Mohali, students will simply write in their feedback. There is not much maths here, and it's all theoretical kind of thing. Where is all this really high-powered maths and all that? Then I photostat some of these derivations of complex formulas, everything from the book, and send them as a email attachment. Then this, oh, I see. The point is, statisticians have done all that. Now, why do you want to bother? They give you the tool, you use it instead of saying how the tool is made, right?
Actually, sir, I think that if it is not made by some biologist, then we can have faith. But if the table was made for for commerce student, researcher, or for economist, or for like social science purpose, so will the same table can be used for the biological data set?
See, the T table is a discipline neutral. Okay, it is a statistical concept. It is a statistical derivation. And what the statistician says is, you can apply these T tables anywhere you find it useful, whether it is in psychology, linguistics, education, bioeconomics. So it's a T table to evaluate the probabilities. It's entirely based on probabilities. So wherever you're talking about probabilities, T table comes in, whether it's in economics or linguistics. But if we are talking about some superstitions or some such thing, there is no question of probability. Either you believe it, you don't believe it. Right? So then you say, oh, I don't need this. Then you say, oh, I don't need these T tables. I know for this happens.
Okay, sir.
Right? So, wherever, you have probability, life is full of probabilities. Right? So then you look up what is the probability.
Thank you, sir. And it is always a treat to listen you. And I think now there is no more question. So now it's time for vote of thanks. So
Sabith, I would be very happy to get some feedback from the students. Feedback. Unmute. Yeah. You're okay now. I can hear you.
sir, okay, sorry. I was on mute. Okay.
Yeah.
So what I was saying, sir, that assessment form.
Right.
So feedback portion, we have some question like their knowledge before your lecture and was it tough, different like feedback, the typical feedback form.
Sure.
So, and we have also given some point so that they can write freely what they want from us and
Exactly.
what they want from our speaker.
Totally anonymous, you have to collect.
Yes, sir.
And because I feel that there's always an improvement that I could make based on students' feedback.
Sure, sir. I will share the data with you, sir.
Sure.
But it will take 1 week because
No hurry.
Okay, sir.
No hurry. Huh?
Okay.
Okay. Thank you very much. Thank you, guys, all the students. I hope you found something useful in my lecture.
Yes, sir. Oh, very useful, sir.
Sir.
Very useful and interesting, sir.
Thank you. Bye.
Sir, give me chance for vote of thanks, sir.
Oh, right. I'm sorry. Go.
So, on behalf of the organizing committee, I take this opportunity to express my heartfelt gratitude to all those who made this event a success. First and foremost, our sincere thanks to Sir for gracing the occasion with his presence and sharing such valuable insight about the test of hypothesis. We are truly honored, sir. I extend our deep appreciation to Principal Sir Professor Narendra Singh, whose guidance and constant support made this program possible, to the IQAC coordinator, Professor P.K. Susodia, and the bursar of the college, Professor Mukesh Jain. I also acknowledge the constant effort of the convener, SDCC, Dr. Saima, and fellow colleagues, Dr. Dheeraj, who ensured the smooth conduct of the session. A special thanks to all the participants who have registered and shown such enthusiastic engagement. Your presence is what gives meaning to this course. Last but not the least, thank you all once again for being with us today. We look forward